Okay, so we've talked about the rotational analog for everything else that we've discussed in this class in the translational sense. We've done the rotational analog to forces, to kinematics, to energy, to kinetic energy. So all we're left with is momentum. To get to a description of angular momentum, I'm going to start with what we know already, which is Newton's second law regarding torques. The net torque acting on an object is equal to the moment of inertia times the angular acceleration. Now, I know what an angular acceleration is. That's just like the change in the angular speed of an object divided by some time duration. And if I write that out in all its glory, that looks something like omega final minus omega initial divided by delta t. Which really just looks like, if I want to be tricky about it and combine my I with the omega, looks like that. So if I rearrange this and write it like so, summation of the torques times delta t is equal to I omega minus I omega naught. The left hand of that equation sort of should look familiar to something else that we've encountered. What does that sort of look like? Yeah, that looks like impulse, right? So impulse was just the force times some duration, some time duration. Well, now we have the rotational analog, which is torque times some time duration. And if you remember, the impulse momentum theorem said that if you had some net force acting on an object over some time duration, then you get a change in momentum. Well, here you have some net torque. What this says is if you have a net torque exerted over some time, you get a change in angular momentum. If we define angular momentum to be the moment of inertia times the angular frequency of an object. So this is just angular momentum. And this equation right here is sort of the rotational analog to the impulse momentum theorem. And they don't even say this, but we'll talk about it again in a minute. Okay? Now, I'm leaving one thing out here, and I'm going to put it back in because it is important. We haven't really emphasized this as we've been talking about all of our rotational things. But all of these quantities that we've been dealing with, torques and angular velocities, those are vectors. And for that reason, just like linear momentum is a vector, angular momentum is a vector. And that's really important. All right? We've talked about how rotation, we only really treat rotations in one sort of direction, so we sort of ignore vectors a lot of the times. You can't really do that with angular momentum, and you'll see why in a little bit. All right, so don't forget that that thing is a vector. But what this equation up here says is that if there are no net torques, then angular momentum is conserved. Just like if there are no net forces, then linear momentum is conserved. All right, and in that case, I can write an equation that looks very similar to what I've written before for linear momentum. L sub I is equal to L sub F. All right, and conservation of angular momentum pops up all over the place in this universe. And so that's why it's pretty fun. So the first place that I want to look at it and talk about is, this stuff sort of applies on a universal scale to orbits of things. And I think that's kind of fun, talking about how objects orbit around other objects. So let's look at one case of that. You can imagine that there's some star and you have a planet orbiting around that star. And that planet moves with some velocity v at a distance r from the star. I can calculate the angular momentum of this system, specifically of my planet. In order to do that, I need to know the moment of inertia of my planet. What is the moment of inertia of this thing as it's rotating about the star? Remember, what's the moment of inertia for just a discrete object? 1/2. No. mr squared. All right, so if you just have a discrete object, it's mr squared. Now, any object is going to have mass times radius squared. The coefficient just depends on the mass distribution. Here we just have sort of like a point object. All right, so I is equal to mr squared. And then we can write down, since this thing is orbiting around this planet, we could write down some angular speed in terms of the velocity. Omega is equal to v divided by r. So if I put that together, I can get the angular momentum, or at least the magnitude of the angular momentum. It's mr squared times v over r. Cross out one of my r's. What I get is m times r times v. All right, so the planet, whatever this planet is, call it Earth, has some angular momentum about this star that's equal to its mass times the radius from the star times the speed of the planet. So the question that I actually am trying to get to here, though, is how does that inform me about the speed of that planet at a different position? So you may know this, that planets orbit stars in elliptical orbits, that's sort of an ellipse. So an ellipse, of course, has, so that means that the planet is closer to the star at one point in its orbit than it is at another point. So the question then is how do these two speeds compare? And I can figure that out. I can see that if I use conservation of angular momentum. If I look at this system as a whole, the planet orbiting the star, there's no external torque applying on the planet. Right? There's nothing else in this picture. So that means that angular momentum is conserved, which means that L1 is equal to L2. I'm going to write it as a vector, but we're not going to care about the vector in this case because there's not going to be any change in the direction of the angular momentum. Right? Angular momentum is typically defined in a similar way to torques and things like that. Our angular momentum here is going clockwise. The plane of our orbit isn't changing, so the direction isn't changing. So what that tells me then is that mass of the planet times r1 times v1 has got to be equal to the mass of the planet times r2 v2. Masses go away, they don't matter. But I do, if I look at this picture, I say, well, r1 has got to be greater than r2. Planet's a lot closer here. So what that implies then, if r1 is greater than r2, in order for those two sides to be equal, v1 must be less than v2. So what this says then is that the closer that a planet gets to its star, the faster it has to go, right, in order to stay in orbit. And that's actually observed. And that's how things actually work, which is good because we'd like our physical laws to actually work in real life. All right? It's kind of a little bit why do you think this is counterintuitive, though? Does that seem a little bit weird? I mean, way out here, this thing's far away from the planet, so it has a lot of potential energy. As it moves closer in, you say the potential energy must go down, so that energy has to go into its speed. So it's still just a conservation of energy problem. You're taking the energy in the form of potential energy far away, and you're putting it into kinetic energy as it gets closer. All right, so it sort of makes sense from the point of view that we've talked about energy things before. All right? So this is all that angular momentum is. Yeah?
So you were able to use the initial angular momentum equals the final angular momentum?
Yes.
It's because there's no net torques acting on the orbit. Is that because, like, it's in orbit, so there's no
Yeah, so what else could there be? So how could I apply a torque to this system, right? I mean, there's no air in space, so there's no friction exerting a torque on the planet. The only other thing that there could be that's messing this whole thing up is like another planet or another star nearby. But we're just assuming that there isn't, and that doesn't matter. Space physics is easier because there's fewer things to get in the way. Nothing this simple. All right, let's do a real example here and apply it. Oh, it's a long example. Lots of writing. All right, so a student sits on a stool while holding 2 weights. And the stool is free to rotate about a vertical axis. Without friction. I'm going to give you the moment of inertia of the stool and the stool and the person and the weights. All right, so we're going to make this sort of straightforward. And that is 2.25 kilogram meters squared, kilogram meters squared. And that's when their arms are outstretched. All right, so the question then is, as the student rotates, they pull their arms in. All right, so you can imagine then you're rotating, this is sort of the classical ice skater problem. All right, you start rotating with your arms out. You pull your arms in as you're rotating. What does that do to your moment of inertia? It decreases because moment of inertia is mass times r squared. If you reduce r, it goes like mr squared with some coefficient in front. If you reduce r, you got to reduce the moment of inertia. So what happens is the new moment of inertia is going to be 1.8 kilogram meters squared. So the question then is, what is the new angular speed if the initial angular speed was 1 revolution every 1.26 seconds? Long question statement, I apologize. All right, so the picture, at least in the starting position, looks like this. They're on some stool, arms outstretched with a couple of weights, rotating like so. Pull the arms in, change the rotational speed. All right, there are no external torques because there's no friction on the axle here. So that means we can use conservation of angular momentum, which says that I omega is equal to I omega. All right, now let me stop really quick here and point out something that's important. When we are dealing with normal momentum, linear momentum, most of the time our mass didn't change. Right? So you had P initial is equal to P final, which meant that mass times V initial equals mass times V final. There's a big difference now, though, between mass, as in linear inertia, and I, as in angular inertia, rotational inertia, because I depends on the radius of whatever object you're talking about. So it is often the case that there is a difference between the initial rotational inertia and the final rotational inertia. So don't forget that. Don't just automatically write down I omega initial is equal to I omega final, because I can change very easily just by changing the radius of the system, or the mass of the system, but often the radius of the system. All right, so we have this equation that we need to solve. What we need to do is figure out what the, we know what the initial and the final moment of inertia is. So all I need to do is plug in my angular speed. I gave you in some weird units, I gave you omega initial is equal to 1 revolution every 1.26 seconds, but we like radians per second, so we need to convert. And this, Chloe, is where 2 pi comes in, because it's 2 pi radians. It was somewhere in there, yeah. 2 pi radians per 1 revolution. So if you do the division, what is it, 5? I think it's 5. 5 radians per second. Okay, so with that, I know everything I need to know, and I can solve for the final angular moment, the final angular speed. It's equal to the initial angular inertia times the initial angular speed divided by the final moment of inertia. So we have is what was the initial was 2.25 kilogram meters squared times 5 rads per second divided by 1.18 or 1.8 kilogram meters squared. All right, do the division, and what you get, and you may know this from experience, that you speed up. 6.25 radians per second.